Bismillahir Rahmanir Rahim. Is there any question from the last sessions? No? Okay. Sorry for delay. Today the server was busy, so I lost sometimes half an hour for the first group, and I had to shift everything in my program. Okay. In the last session, we talked about the structure of internet, and okay. Naima, ask me. If you have question, please ask me. Web server is an end system, yes. Web server is an end system. Yes, everything. You know, end system is a system that runs an application program, a network application, an application that which needs to use internet, to use network for running. Okay, so maybe a switch or a router can be an end system if we look at a router as a system that which is running a network application. For example, when we try to configure a router, a switch on the internet, on the web, on the network. At this time, a router or switch is an end system. But when I'm using a router or switch to route a packet, to forward packets, it's not an end system. So be clear about this introduction, in this definition. An end system use or runs a network application. Does every device have a CPU? No. We have something else. Most of our applications, most of huge devices, the devices with large sizes, are using CPUs, but some devices use ASIC. ASICs are special circuits. CPU is a special circuit. ASIC is another type of CPU. It's a special circuit designed for a specific task. In some devices, we use ASICs instead of CPU. For example, maybe in a small sensor. In a small sensor, we have not enough space to use a CPU and programming it and doing lots of things. For example, in small boards such as Raspberry Pi. If you look on Raspberry Pi, you can see Raspberry Pi has not a CPU, but it has some specific ASICs works, those circuits work as a CPU, like a CPU, similar to CPU. Okay? Naima? Naima? I think. Okay? Naima, okay, sorry. Please write your name in Arabic or Farsi. Arabic and Farsi alphabetic are similar together. I think it's better for me than when I use English. Okay. Is there any question, Naima? Okay. You're welcome. Okay. Last week we talked about packet switching. We said that in computer networks we use packet switching. In packet switching, a network receives a message from application. Then the network breaks the message into some chunks, and each of those chunks are put inside a packet. Inside a packet, and each packet is forwarded through the network, inside the network. At each hub, each switch or routers, a separated net packet is processed, its route is defined, is cleared, is detected, and the router or switch forwards that packet toward its destination. This is the reality in packet switching. We process each packet completely separated from the others. Okay? But there is an alternative for this, for packet switching. It's circuit switching. In circuit switching, we use a circuit. Firstly, we establish a circuit between the source and the destination. And after that, we send the data over that circuit, like a water pipe. Okay? When you open the valves, you can see, okay, the water goes through the pipes. But firstly, we have to create that pipeline. Here, firstly, we have to set up a circuit. This circuit is dedicated, like a pipe. It's a dedicated path. It means that if I set up a circuit for myself, then nobody can use my circuit. If I don't use it, okay? If I don't use my circuit, it's not important. For example, in my home, I don't use my water pipes. It's my own pipe circuit. I am paying for that. Nobody can use it. So we say these resources are dedicated. It means that they are not shared among other users. So the performance is guaranteed in circuit switching. Because I know I have my own circuits, my own resources, I will pay It's not cheap. It's not free. I am paying for that. You know, I'm paying lots of money for that. But I know the qualities, the performance is guaranteed because I know this is a dedicated service for me. Wait a minute, please. Wait a minute. Sorry for interrupting. Okay. For example, for example, let's suppose let's think about traditional telephone networks. Traditional telephone networks are using circuit switching. I'm hanging the phone, okay, dialing someone, and I'm waiting after uh, pressing keys, phone number. Okay, I'm pressing call button, and after that I'm waiting. After a while, in a few seconds, I'm hearing beep or beep 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 beep, something like this. What does it mean? When I'm hearing beep, a continuous beep, something like this, beep, it means that the circuit is established, and I should wait for the other side to raise the telephone to answer me. But the circuit is established. Beep means the circuit is established. But when I'm hearing beep 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 beep, something like this, it means sorry, I couldn't finish the circuit. I couldn't set up the circuit. Something went wrong during this setup. So I have to try again because the circuit does not established. Okay? Because of this, using this strategy, using a dedicated circuit, you can see traditional telephone networks are not cheap. You should pay lots of money each month for telephones. But this strategy is not good for computer networks, for computer applications. Why? For example, I want to read some news. Okay, so I'm entering URL of a news website and pressing enter. Okay, then after that I'm reaching the home page of the news agency, and I'm selecting, for example, 10 topics in the website to read, 10 news. Okay, click open in new tab, and I'm opening 10 web pages. Let's suppose that I need to spend 1 minute to read each of those news. I open 10 news and I'm spending 1 minute to read each of them. So I have to spend 10 minutes to read those news. Okay? But what will happen during these 10 minutes? Nothing. Why? Because I'm trying to read. I don't use the networks. So it's empty. If I use circuit switching technology, during these 10 minutes, I have to pay. I know that I don't use the circuit, but I have to pay. Why? Because the circuit is for me, established for me. It's my problem. I should pay. Because it's a circuit switching technology. It's circuit switching technology. Okay? I have to pay. But so circuit switching technology is not good for computer applications. Why? Because most of the time I never use my internet links. I'm on the web, on internet, but I don't use it. I'm reading, I'm doing something else. I'm waiting for a message. I don't know. Just my link is free. So why should I pay for that? Circuit switching could not answer this problem. So we try to go through packet switching. Okay. One main question. Okay, I said that we should set up a dedicated circuit for each user. How? How we can create a dedicated circuit? We have two main categories to this. The first one is using frequency division multiplexing. The second one is time division multiplexing. In frequency division multiplexing, we have a bandwidth, a large bandwidth. For each user, we define a specific range of frequency. For example, here we have 4 users in different colors, okay? Pink, orange, green, and blue. And we define a specific frequency ranges for each of those users. We can see they are separated completely. This is frequency division. We divide a large bandwidth between some users, based on their needs. Okay? For example, when you are hearing a radio, for example, you are trying to hear specific channels in radio. Okay, you should change your frequency, the frequency of your received frequency in your radio, to a specific one. It means you are trying to change the frequency band to go to a specific channel. When you are watching TV, again, if you try to look, for example, channel 1, okay, you should change your frequency band into the frequency band of channel 1 in your TV. I know you don't see it in current TV, but the TV will do it for you. When you try to search for TV channels, it finds the channels of different frequency band of each channels. Okay, and then when you ask, okay, show me channel 1, the TV changes the frequency band into the frequency of channel 1. Each user sends its data over its channel. This channel is dedicated. On the channel of channel 1 in TV, I cannot hear, for example, channel 1 of radio. They are separated. They are dedicated. Okay. The next one is time division multiplexing, TDM. In time division multiplexing, we define a time window and then we break the time in this time window, time window or time frame. We divide times in different slots. For example, for class scheduling in the university. Okay? In class scheduling, our time frame is a day. For example, Saturday. We know that each class has 1.5 hours time. So from 8 to 9:30 there is a class. From 9:30 to 11 there is another class. From 11 to 12:30 another class. From 13 to 43 another class. We have different time slots for each class. Each of them has a width of 90 minutes or 1.5 hours. We divide the time. Our resource is a class, okay? And we divide the time of this class. So each course can use that class in a specific time. And we know that, for example, at this time, we have a computer networking course, and you cannot, at the same time, you cannot have another course. It's dedicated. Other professors should join today's class in other times, not at this time. So our time is dedicated. In time division, so we should define our time frame and we should divide the time frame into some time slots. And then we can assign each time slot to a user. Different time slots, different users. Okay? If someone needs more time, we can, for example, assign him or her 2 time slots, 3 time slots. I don't know. It's not important. Or in FDM, we can assign, for example, a wider bandwidth to a user if he or she needs more bandwidth, or he or she, if he or she needs a narrow bandwidth, we can narrow his channel. It's not important for us. Based on their users' need, users' requirement, we assign a dedicated amount of resources or bandwidth to users. Okay, let me compare packet switching vs circuit switching. Suppose that we have n users in a network. This network is connected to internet through a 1 gigabit per second link. Okay, and each user needs 100 megabit per second bandwidth. If I use circuit switching technology, I can service, this network can service 10 users. It cannot service, for example, 11 users, 12 users. Maximum capacity for this network when it uses circuit switching technology is 10 users. Why? Because each of those users receives a dedicated portion of 100 megabit per second. So it can serve 10 users at max. 10 users, nothing more. But when we use packet switching never says no. It never says. For example, let's suppose 35 users request to send data over the network. If I use binomial distribution equations, I can prove that with probability of 0.0004, the network with packet switching technology can answer 35 users. I know that this probability is close to 0, but it's not 0. This is very important. It's not 0. It can answer the requests, but with the probability near to 0. This is the big difference between packet switching and circuit switching. The packet switching never says, okay, I could not answer you. He says, okay, let me try. Inshallah, I will serve it. Inshallah. It's a big difference. Why? Because in computer networks, computer applications, we never send or receive data continuously. Just sometimes we send some data. Just sometimes. For example, right now I have a class. We are joining in a class. So we'll be sending or receiving some data. But what will happen after that? Nothing. All links became empty. It's obvious. This is the behavior of computer applications. Packet switching is great for bursty data. What does it mean? It means that computer applications just only use a small portion of time for sending a large amount of data, a huge amount of data. Now we are spending 1 or 1 hour, 1.5 hours in our class, and we send or receive a huge amount of data. After that, it's finished, and all links became empty. If I use circuit switching, I cannot handle bursty data because bursty data just arrive in a special time. times. Not always, just in a special amount of times, just sometimes. We have a great burst data, a great amount of burst data. And at that time, in packet switching, we have shared resource and it's simple. There is no call setup or something like that. Because if you try to use call setup, you should wait for setup. Wait to setup became complete. But what I can do during this time is what can I do with a large amount of received data? Nothing. I should create a buffer to store them. Why? Packet switching says, okay, send them. They will receive to the destination, inshallah. Just send them. So packet switching is great for computer applications. But in packet switching, excessive congestion is possible. It's possible. Why? Because as soon as arriving a large amount of data in networks, queues would be full. So, if they became full, traffic. We say a congestion rises. We should handle congestion. So we should define some extra protocols to handle congestions. During congestion, packets spend lots of time in queues before receiving their services, before we serve them. And maybe some packets became lost. Maybe. So maybe buffers became overflow. So network congestion is not good. We have to be care about them, and we should use several packet queuing techniques to manage congestions in computer networks. Yes, when we talk about buffers, it means memory. Buffer is a memory. When a burst arrives, all of memories or buffers became full. And what should we do after that? Because they are full and I couldn't accept new packets on them. So I should say, okay, sorry for that, but I should drop this packet, which is not good. A packet arrives after a long time and simply I drop it. It's not good. But as I said, when we use secret switching, there is a guarantee in packet switching, guarantee in performance. But in packet switching, we cannot guarantee it. What should we do? We can create a new type of networks. We call it virtual circuit. In virtual circuit, we create a new and a specific packet switching network with behavior of circuit switching. A circuit-like behavior, but those circuits are not dedicated. If we can, if the circuits are empty and nobody uses them, we can share them. So in virtual circuit, we create a circuit-like behavior in packet switching. We will talk about these topics in the future. There is a quality of service. Let me start another topics. We say that internet structure is a network of networks, a collection of connected networks together. They are connected through ISPs or through internet service providers. ISP, internet service providers. I'm connecting to internet through an access ISP. So that access ISP must connect to other parties in the network, in the internet. Some ISPs are local, some of them are regional, some of them are national, some of them are global. You know, there are several types of ISPs. We will talk about them. But I know that ISPs are some bridges. Connect me to the other parties in the internet. Connect me to you. We are connected through passes created by those ISPs. How two ISPs can connect together? It depends. For example, based on national policy, I cannot connect an ISP in Iran to an ISP in Israel because Iran and Israel are enemies. So I cannot connect an ISP in Iran with an ISP in Israel. But what about an ISP in Iran and with an ISP in Iraq? What about this? Iran and Iraq are not enemies, so according to national policies, they can't connect together. At this time, economics became important. Is it economy? Economical? Or is it economic to connect an ISP in Iran with, if you know something else? Okay? We should look for other um, approaches to create a circuit between Iran and Iraq and pass a communication pass between these two countries. So it depends. Between nations, national policies are important. Inside a country, or between some countries, is important. Okay. Let me go into this structure, go deeper into this structure. Look at this. We are connected to access ISPs. We are connected to that is impossible. So instead of that, create network. A better option is this. Instead of having global ISPs, each of them serve to some, and then those global ISPs can connect together in two different ways. One way is using peering links. Peering links means that two ISPs are connected together, and upon an agreement, they say, okay, I'm sending your traffic, and instead of that, you send my traffic too. I never charge you, and you never charge me. So freely, without money, with no charges, I'm serving to the other side, and he or she serves me. Okay, this is a peering link. But the other link is internet exchange point. Upon some policies, and here in IXP points, we have to pay. It's a business, and there are several competitors here. So we can connect those ISPs together using peering links or using IXP points. Okay, here you can see those links between ISPs in red, with lines in red. This means that these types of, for example, look at here, there is an IXP point between three different ISPs. Okay. As you can hear, these links are special with very high bandwidths. And inside of these ISPs, we can see very powerful and big routers or switches. The most powerful routers or switches are used in these big ISPs. Here, we call them content provider networks. What is a content provider network? Like, for example, Google. Google has several data centers distributed all around the world. In those data centers, there are huge amount of traffics and files stored on those data centers. So Google saves a great amount of content. Google, Microsoft, Amazon, Akamai, Sony, Facebook, Twitter, Telegram, WhatsApp, all of these companies, all of them, they have content. They have content provider networks, some special networks to save and present stored content by other users. And you can see here that these content provider networks are in the core of internet. They are global. They need to be placed here. They need links with high bandwidth, to serve their traffics as soon as possible with the highest amount. Look at this structure. In this structure, you can see structure of internet. It has several tiers. The topest tier is tier 1. There are just a few companies stand in tier 1, stand as tier 1 ISPs. For example, Sprint, Level 3, AT&T, NTT. There are just a few companies in tier 1. They are creating the core of internet. Main links in internet are in their domains in tier 1. And you can see, for example, but Google sits at the same level with tier 1 ISPs. Google, Facebook, Twitter, I don't know. So they are standing in tier 1 level. And using some IXPs, you can see tier 1 ISPs are connected to regional one or regional ISPs, local ISPs level. But sometimes they are connected to directly. They are connected to, for example, tier 1 ISPs. Okay. This is the real structure of that from my computer to your computer. I'm sending my data to an access ISP. It sends my data to a regional ISP. It receives to the server, and after that, the data sends from an access ISP to a regional ISP, maybe to a toward, and you can this is internet through these tiers, these different tiers here. We have 2 or 3 tiers in the internet, as we can see here, through these ISPs toward the destination, from the source toward the destination. Okay, that is enough for today. Is there any question? IXP, and I'm IXP connect ISPs in the lower tier toward the ISPs in the if we decided to, in tier one, between tier one ISPs here, the links between tier one ISPs are peering links. They are free. It means that I'm serving your traffic and you serve my traffic, and all of these serving are free. But when we serve to send data from a lower layer, a lower tier, to a higher tier, we are using IXPs to send data to the best tier, to the best ISP. And here we pay money. This is the big differences. When we use internet services, we are paying to access ISPs, and for you until the next session, and have a good day and goodbye.